Okay, welcome to the second part of the tutorial. In the morning we talked about, or before the lunch break, we talked about visual place recognition. We're very interested in getting an approximate position and orientation for a query image. And here in the second part of the tutorial, we'll talk about accurate camera pose estimation with respect to some scene representation. And in this first part, the scene representation will mostly be a 3D model of the scene. And the second part that Alex will talk about, the scene will be represented implicitly by a convolutional neural network. So the approaches that I'm going to talk about are feature-based in the sense of, given a 3D model and a query image, the first step is to establish a set of 2D 3D matches that link pixel positions in the image and 3D points in the 3D model or 3D point cloud. And then once you have those, you can estimate the camera pose using pretty standard techniques that involve applying an endpoint pose solver that computes a camera pose from n 2D 3D matches inside a Ransack loop to handle outliers. So you end up with a camera pose such that the 3D points are projected onto or close to the 2D measurements. The classical way to getting those 2D 3D matches is to build the 3D model from structure for motion. So here you see a point cloud, and each red pyramid corresponds to one image. The points are reconstructed by essentially triangulating local feature matches. So you end up with a 3D structure where you can associate each 3D point with one or two or more local image descriptors. And you use those local image descriptors then to establish the matches. An alternative to this very explicit representation is to learn this mapping. So here at CVPR there was a pretty exciting paper on given an input image, regressing the 3 point coordinates for each pixel in the image, and then using those matches for pose estimation. But I'm going to talk about the former kind of methods. I think Alex is going to talk a bit about this learning-based approach. So obviously, one question is, why do we bother with those explicit representations? Why don't we just, in the age of deep learning, use CNN that takes an image as an input and then gives you a 6-degree of freedom pose? And the answer is pretty simple if you look at some experimental results. So this is median position and orientation errors for a bunch of data sets. This is the best CNN-based methods that's out there, so that's not a single method, but the best results obtained from multiple methods, or at least those methods that I was aware of that I could find in conferences and on archive. This is a rather simple priority search approach that I'm going to talk about later, which is significantly more accurate than the CNN-based approach. And those are some results from this differentiable Ransack paper that was presented here at CVPR. Some of this is preliminary, and Eric Brackman, the first author of the paper, was kind enough to share those results. But they indicate that you can get a much higher pose accuracy using explicit feature correspondences between pixels and some 3D scene points, and then estimating the camera pose. Sure. Is that better? In general, if there are any questions, feel free to ask me. I'm happy to answer everything. Okay, I'm going to talk about a couple of things. I'm first going to talk about efficient localization based on prioritization, where the idea is you would like to get those 2D 3D matches that you need for pose estimation as efficiently as possible. The next step then is to take those approaches and scale them to large scenes, for example, city scale. And then the third topic is essentially also a scalability problem, but not to larger scenes, but to devices, mobile devices with limited memory and compute, under the additional pressure of trying to get things to run in real time. And then the last topic is a challenge or a new benchmark dataset that we are going to release soon on Archive on day and night matching, and that we are pretty excited about. So let's start with efficient prioritized search. And before we get to that, let's introduce a very simple baseline approach. So what this baseline does is, given a 3D model where each 3D point is associated with a descriptor, it builds a search structure in descriptor space. And probably the most common, most well-used search structure is a KD tree. That's just binary space partitioning. Given a query image with associated image features, you walk through that tree, get essentially the nearest neighbor and a second nearest neighbor, and then you apply Loewy's ratio test, or the SIFT ratio test. The idea of this ratio test is that you measure the distance to the nearest neighbor and to the second nearest neighbor. If they're about equal, then you're somewhere in between and don't know which one is the correct neighbor. So what you want to do is you only establish a match between the query feature and a 3D point if the descriptor is sufficiently closer than the descriptor of the second nearest neighbor. Once you have those matches, you do camera pose estimation, and then in the end you do have to make a decision, which is do I accept this pose, or do I believe this pose is correct or not? And this is typically done by looking at the number of inliers of that pose and then putting a threshold on this. And historically this threshold has been 12 inliers, but you could also use higher thresholds to get a higher confidence in your estimates. So how well does this work? Here's a couple of results on some standard benchmark datasets that are essentially solved by now. So this is the Dubrovnik dataset from the Building Rome in a Day paper. And the x-axis is the time required to localize an image, excluding feature extraction. And the y-axis is the number of localized images. The top of the y-axis is the number of query images in total of this dataset. So you see that you can nearly localize all images if you're willing to spend like 3 seconds per image. Here's another dataset, slightly larger, where again you get most of the images, and again you will need to wait a couple of seconds. And here's the last dataset. It's a bit more challenging, where again you actually get pretty good performance at the price of runtime efficiency. So overall you get pretty good localization effectiveness in terms of the number of images that get localized at the price of being slow. And this part of this talk here is now on getting the same localization effectiveness at an order of magnitude less time. So that's the idea of making things as fast as possible. And the key observation here is that you don't need to get all matches that you can get to get accurate camera poses. You can just find a subset, and if you can find the subset efficiently enough, then you can accelerate the matching stage, do pose estimation, and still get a good pose estimate. And we're going to talk, there's a bunch of work on this. We're going to talk about a simple greedy strategy for efficient prioritized search that also performs well. And I'm going to give you an overview of other methods later. So the simple strategy is you try to find the search costs that you need to pay for each feature. So how many descriptor comparisons you need to find this nearest neighbor, and then you just prioritize based on the search costs. So how do we find those search costs without actually doing the search? The idea is simple. So if this is your descriptor space, dots are 3D point descriptors, and stars are query descriptors. You quantize the space into visual words using k-means clustering. And then for each query feature, you would restrict the search to its cell. So for the ping feature, you would look into the pink cell, and you would need to do 3 comparisons. And you can actually figure out how many comparisons you need without doing them, because offline you assign the 3D point descriptors to those visual words, and then just store the number of assignments. For the green feature that would fall into a different cell, you would also do 3 comparisons. For the blue one you would do 2, and for the red one you would do 5. So this simple greedy strategy then just orders the query features based on the search costs from cheap features to more expensive features, and then stops search once it has found n, typically set to 100 matches. So the resulting order that you would get here is, you would start with the blue one, where you only need to do 2 comparisons, continue with either the green or the pink one, and then do the red one last. Yes? So the question was, how do you represent the descriptors of the 3 points? Do you use one descriptor per point or multiple points? The easiest strategy is to use a mean descriptor. What we ended up using here, or what works better, is to first do the assignment of point descriptors to cells, and then for each cell compute a mean descriptor per point. So if you have 2 descriptors falling into the same cell, you take the mean of this. This is requires about 2/3 of the memory that you would need for all of them, but gives you better performance. Another nice property of this prioritization scheme, besides doing search based on how costly search is for each feature, is that it's actually a natural ordering, because the number of points that fall into a cell kind of correlate to the uniqueness of this visual structure. So you would start with structures that are more unique first, and then end with things that are more ambiguous. And this kind of makes sense. You would first look for unique structures in an image, and then if you can't find anything for them, you continue to less and less unique structures until you end with repetitive elements. So in this sense, it's similar to the classical inverse document frequency weighting used in image retrieval. A bit more formal, this vocabulary-based prioritized search can be visualized as such. So you first assign the 3 points to visual vocabulary. For the query image, you first compute the assignments on runtime. Then for each feature, you essentially do a lookup on how many comparisons do I need to do. You sort those features based on the costs. And then you go through the features one by one. So you do a linear search through each element in the cell. So for the first one, the orange one, you find the 2 nearest neighbors, apply the ratio test. And in this case, the 2 nearest neighbors have about the same distance, so you wouldn't create a match. For the red one, you again find the 2 nearest neighbors, perform the ratio test, and in this case you would decide, oh, the first nearest neighbor is closer, so let's accept this match. And so on and so on. You would go to the pink one, get a match, go to the blue one, get a match, and then at some point you decide, probably have enough matches, let's just attempt post-estimation. And typically you stop after 100 matches, where 100 comes from looking at how many images can I localize with different thresholds on the number of matches, and then choosing the smallest one that gives you good performance. If you compare this to the KD tree-based approach, then the good news is that you get significantly faster, up to an order of magnitude faster actually. But at the same time, you also lose images that you could localize before. So you can see this both more on Dubrovnik and Vienna. So there's a significant drop in the number of localized images. And the reason for this behavior is actually pretty easy to explain. We quantize our search space, and we only search through one cell. So in this example here, the 3D point corresponding to the green query feature lands into different cells due to quantization artifacts, and you will not be able to find this match. And there are some obvious strategies of resolving this problem. You could use a smaller vocabulary, which reduces the quantization artifacts that you observe. Or you could search through multiple cells. So that's a standard approach in image retrieval to lessen the impact of quantization artifacts. The drawback of this is that you need to pay a higher search cost for each feature, even those where you previously could get a match. And on average, the number of points that fall into a visual word increases linearly in the number of points. So then an obvious question is, can we do something more efficient? And the answer is yes, we can, by exploiting the fact that feature matches do not occur individually, but there's a structure to them. So the concrete idea is to exploit the co-occurrence of matches. So what do I mean by this? If you look at this example, let's assume that the pink feature matches to a point. If this match is correct, then I would expect that I can also find matches for some of the surrounding 3D structure. Think of a single match as a hypothesis of which part of the 3D model is visible in the image. So you can actually look at the local neighborhood of the matching point and then say, if this match is correct, I would expect, I would expect to also find a match for the green 3D point and then match it back to the image. Implementation-wise, this looks like this. So you would do a vocabulary-based prioritized search where you would go through a search structure to end up in a visual word where you would do your nearest neighbor search. And while you traverse this tree, you also remember in which through which nodes you went. And if you use a vocabulary tree, each intermediate level corresponds to a visual vocabulary on its own, which is smaller and thus has less quantization artifacts. So you remember this, and you do this not only for one feature, but for all features. So you would have an assignment of the input features to a smaller vocabulary. The nice thing is you get this for free because you need to go through the tree anyways. Then if you want to match back the green point against the image, just go up a couple of levels, figure out in which cell of the smaller vocabulary do you go to. And again, this is pretty easy to do. There's the traversal is deterministic, so it's just to look up. And then you can just do a nearest neighbor search, find the two nearest neighbors, do the ratio test and decide whether you want to have a match or not. So this integrates pretty nicely into an existing framework. It reduces the quantization artifacts by just using a smaller vocabulary. You can reuse the data structures that you have to build anyways. And you can also still do prioritization, because matching from 2D to 3D and from 3D to 2D is just a number of descriptor comparisons. You can do an easy lookup for both directions, how many comparisons you need to do, and then you just sort based on the number of comparisons. You can also show that this scheme is more efficient computational-wise, or in terms of complexity, than multiple words assignments or just using smaller vocabulary, but I'm not going to go into this. If you compare, yeah? Yes. So what I do is I first identify points that are close in 3D space to a matching 3D point, and then match them back. So the idea is, think of you're somewhere in Paris, say you're looking at the Eiffel Tower. So you get one match onto the Eiffel Tower. If this one is correct, you would expect that some of the neighboring geometry is also visible in the image. So you take nearest neighbors in 3D. No, okay. It's in, this is in descriptor space. The selection of the candidates that you use for backmatching are in 3D. Yeah. Yes. Yes. So you would select this green point because it's close in 3D space to a matching point, but the matching itself would again be done in descriptor space. And you could do this more efficiently by exploiting the fact that locally geometry should be more or less approximated by a fine transformation, so you could do some predictions there. It's just not done here, but there's things that you could do. If you compare this this method with KD tree search and this vocabulary-based parameter search that I talked about first, so you see that you get a similar or better performance in terms of the number of localized images compared to the KD tree. So this additional active search step helps you to get more correspondences. But also, if you look at it in more detail and compare it against VPS, you see that this increase in localization effectiveness comes at a price of runtime costs, which is natural because you do more work. You do a backmatching compared to not doing a backmatching in the first place. The good news is that you can actually avoid quite a lot of this additional work if you're clever. And if you're clever here means by exploiting visibility information. And this visibility information that you use is encoded in a so-called visibility graph, which you get for structure for motion. So this visibility graph is a bipartite graph where one set of nodes correspond to the 3D points, the other set of nodes correspond to the cameras that you use to reconstruct the scene, and you have an edge between a point and a camera if this camera observes this point. And this structure, visibility graph allows you to reason about co-visibility of points. So two 3D points are potentially co-visible if there's one camera observing them together. So this is essentially a discrete approximation to the co-visibility relation between points, discrete in the sense of that you only have a discrete set of viewpoints. And you can use this graph for filtering. So for example, if you think of this proposal step of active search where you look for additional potentially visible points, what you do is you do nearest neighbor search in 3D. Nearest neighbors in 3D doesn't necessarily guarantee you that this point is visible. For example, in this here, you would have two gray points would be on the back side of the building while you're looking at the front side. And you can infer this visibility relation by looking at the visibility graph. So for the matching point, you figure out what are the nearest neighbors that are co-visible, and then you only take those and forget about the others. So that prunes out candidates that you would need to consider otherwise. The second step that you can do is you can identify wrong matches before you run post-estimation. So imagine those are the matching 3D points that you can get. Those are the database images that observe them. And you see that if you take those database images into account, you get a couple of connected components in this visibility graph. And assuming that the largest connected component corresponds to the correct matches and everything else is outliers, you can just reject, just only take the matches in the largest connected component. And if you do those two optimizations, you can essentially increase the runtime performance without decreasing the effectiveness and the number of localized images. And then if you do some implementation polishing to make sure that you're cache efficient, you can get something that runs twice as fast, I think. So you get something that actually has a good performance at little runtime overhead. Yeah. Yes, those are all timings after feature extraction. So feature extraction, if you do it on a GPU, SIFT GPU, it's, depending on the image resolution, about 100 milliseconds. But this is an individual CPU core. And you could, most of this you could easily parallelize. Yes? To some degree, yes. To that degree that your feature detector gives you repeatable key points. So as long as SIFT is able to redetect the projection of the 3D point, you're good. But if it's too large for SIFT to handle, yes, then it will kick out things that you would like to keep before. Okay, to finish this part, there's quite some work on this. There's work on prioritized matching from 3D points against the image that I didn't talk about. There's a neat discussion about when to use 2D to 3D matching and when to match in the other direction. And this idea of combining both search directions is not exclusive to this active search paper that I presented, but it was also used in slightly different forms by two other papers published at the same time. One where you use 2D 3D matching as a seeding for the backmatching step and only do backmatching. And the other where you do 3D to 2D matching only if you don't get enough matches to for pose estimation. So you would only do it if pose estimation fails. There's also some nice work on modeling matching as a classification task. So you would train a random forest or a set of random ferns to classify each feature to belong to its 3D point. And this can be done very, very efficiently. So the second part then is about outlier filtering. And if you recapitulate prioritized matching, the idea was that given a query image, you try to find correspondences based on a descriptor match. And at small scale, this works really well, or medium scale, because there's at most one unique match. But if you go to large scale, then most likely there are multiple local structures with the same appearance. And this essentially violates the central assumption of this ratio test that you get a unique nearest neighbor, and that if you're not unique, then you have a wrong match. If you have identical structures, a ratio test will always fail. You'll start losing matches. To some degree, this active back searching step can recover matches. So imagine that you have an additional feature and you get a unique match for this, and you do the nearest neighbor search in 3D and the back matching. Then you recover this match because you're not aware of this global ambiguity in the query image. But the problem is that getting this unique match in the first place is hard. So what's typically done then is that you will accept more and more wrong matches to make sure that you recover enough correct ones. But this then causes problems during pose estimation, because standard approach of RANSAC, of randomly sampling sets of matches, doing pose estimation, evaluating them, has an exponential increase in the number of samples that are needed with the outlier ratio. And the operating point that you would work on at large scale is at this back end where you have 20% correct matches or less, or even 1%. So you would it would take ages to get a pose estimate. And if you're working in large scale, you're thus trying to do outlier filtering before you do ransack for pose estimation. And there's a bunch of interesting strategies that I'm going to talk about in this part. So the first here is, first one is based on the insight that not all ransack samples are meaningful. So if you assume that you take those 3 points as part of the 3 matches that you take in ransack, then you would know that the pose that you get will not be meaningful because those 3 points are not co-visible. This leads to a very simple alteration of the sampling scheme used by ransack, where you include co-occurrence information for the sampling. So the idea is that you use information which database images observe a point to guide your sampling. The first sample that you draw is random uniformly, so for example this point. Then afterwards you would randomly draw a point based on all points that you selected before. So in this case you could only draw from those points that are co-visible with the red one. You draw one randomly, say this one, that further reduces the set of points that you can draw from, and then you quickly converge to a set of matches that you can use. The problem here is that that still doesn't resolve this exponential increase. And at CVPR 2014 there was a very nice paper on a deterministic outlier filter. There's also a PAMI 2017 version of this paper. And it's based on modulating pose estimation as a registration problem. So the idea is you would like to find a pose so that the 3D points project close to the image measurements, which is the same as saying the 3D points need to project into a cone defined by your inlier threshold. So you could model this in 3D, saying give me the pose so that the maximum number of matches fall into their respective cones. But you can also simplify this problem by making a set of reasonable assumptions. And the reasonable assumptions that they make in this paper is that they assume they know the gravity direction, so that's what you get in a standard mobile phone, and they assume that you get the ground plane, or an estimate of the ground plane, which at least in urban environments is also a simple assumption. And then they had this very interesting insight, which is, given that you know the height of the camera, you get a distance of the 3D points, or interval of distances. So, assuming that you know that the camera is above the ground at height hc, and since you know the 3D reconstruction, you also know the height of the 3D points above the ground. And in order for this 3D point to fall into this cone segment, it can't be closer than a certain distance, and can't be farther than a certain distance. Otherwise, it would be outside of this cone segment. And the same for all other 3D points. And since you know gravity, and since you know the ground plane and you know the height, you only have to solve a 2D registration problem where you estimate one rotation of ground gravity and a 2D translation in a plane parallel to the ground. So you can actually model this as a 2D registration problem where you try to find a mapping from world coordinates into local camera coordinates so that each point is mapped into this slice through the viewing cone. So you try to find this transformation. Obviously, the height of the camera will most likely not be known precisely, but typically you get a good approximation there. And you can then translate the uncertainty on the height as an uncertainty on the distance of the 3D point. So saying you know the height of the camera up to a certain interval is the same as saying my 3D point has to fall into the cone in a certain height interval, which gives you a new minimal and maximal distance. And if you then go back to the 3D to the 2D version of the problem, you essentially get a set of slices through this volume, which you can approximate by just placing a bounding box around it. And then you try to find a registration that maps the points in 2D into those bounding boxes. Unfortunately, I mean, this is a very neat geometric insight, but it's not enough to do efficient post-filtering. So you would still need 2 matches to get a 3 degree of freedom transformation, which means that if you exhaustively go through this, you need n squared for sampling all pairs, and then an additional factor n for verifying. A fast alternative is actually doing outlier filtering, where the idea is that assuming one match is correct, you try to figure out how many other matches can be correct if this one is, and then reject the match if it's not consistent with enough data. And then afterwards you would do post-estimation on everything that's not marked as an outlier. And I'll talk about 2 outlier filtering approaches based on the same idea. They have runtime n squared log n and have linear runtime in the number of matches. The first outlier filter, this n squared log n, is from the paper that I've been talking about, and they make a neat insight, which is assuming that a match point P is an inlier to the correct transformation, you can find a slightly different transformation or slightly different pose, so that P has a 0 reprojection error and all other inliers have a slightly larger but bounded reprojection error. So you can find a transformation of those error shapes. So one error shape is essentially just a point. All other error shapes are slightly larger. And you can use this then for outlier filtering. So for each point, assuming that P is correct, this point fixes your translation of the transformation. So you only need to rotation. And for each other point, you can try to find the rotation interval so that it becomes an inlier. So what you exploit is that you know the distance between P and this other point that you want to evaluate. So you know that this other point in local camera coordinates has to lie on the circle. You try to find the interval on the circle, rotation interval, so that the point would fall into this arrow shape, or where the circle intersects this arrow shape. And then you record those intervals for each point. So for the second point, you would also get an interval. And then you find the rotation interval that maximizes the number of inliers. Get an upper bound on the number of inliers, and then reject a match if this upper bound is below a certain threshold, say 10 or 12 inliers. And this works well, but the drawback is that you need to go through all pairs, which is n squared, and computing this minimum interval requires sorting, so it's n log n, so you end up with n squared log n. You can go to an optimal complexity in terms of the number of matches if you approximate this procedure through voting scheme. The idea here is that rather than computing an arrow shape for the point in local camera coordinates, you try to have an arrow shape for the camera in global coordinates. The drawback here is that this point would only give you one match only gives you distance between a camera and a point, but and you don't know where this camera is around this point. In theory, it could be anywhere on the circular element. But if you would know the direction in which the camera is looking, then this fixes your position as well. So assume that you know the viewing direction of the camera with respect to an arbitrary axis. And also assume that you know the intrinsic calibration, so you know the angle between the viewing direction of the camera and the ray that observes the point. Then there is a unique circular element on this on the circle where the camera has to be. And those 2 observations are enough to do a voting scheme where you would first quantize your set of camera positions, and then you just iterate over intervals of height. Each height gives you the distance between the camera and the point, and then you iterate over a discrete set of viewing directions, and for each match and a viewing direction and height, you essentially get a vote for a position. And then you keep track of the position that observes the highest votes for all parameters, and then essentially take this position, all corresponding, the points that voted for it, and then you run pose estimation. The nice thing here is that you can typically find a discrete set of heights, a discrete set of, or a constant set of orientations, and then you only need to go through, for each combination, go once linearly through that interval. You once vote for a pose that's also constant time, and then just getting the position with the largest number of votes is also linear. So you end up with something that's linear in the number of matches that you put in, which, if you compare it to n squared log n, is a much better computational complexity, meaning that you can pipe in quite a large number of matches. And if you compare this on a landmark recognition task, so that's the black dot on the axis, so the x-axis is the recall in terms of correctly recognized landmarks, the y-axis precision of this recognition task, and you get the curves by varying thresholds on the number of inliers. Then you see that both this voting scheme and which is approximate, and the exact solution gives you about the same. It's, I think, a 0.5% difference in terms of performance, and this performance is better than previously published methods. And that naturally leads to the question how we solved the localization problem by doing exhaustive outlier filtering. And the unfortunate answer is no, we haven't, because if you just take more matches, then deciding when you get a correct pose becomes a hard problem. And that I will quickly illustrate this in the next slides. So standard approach is you get a pose, you look at the number of inliers. If it's above a certain threshold, it's correct, otherwise it's a bad pose. And this works at some scenes. So here's an example where you get a pose with a certain number of 47 inliers. Left is a query, right is a database image observing those points, which and typically would say 47 inliers is a good number, that's correct. At large scale, you can have structures that have a similar local appearance, similar geometry, and that by chance have more inliers. So here's an example where you can actually get more inliers for an unrelated structure, meaning that you would actually say this is a much better pose estimate than the correct one. And this is something that we call geometric bursts, and can happen in multiple variants. So this is one where you just get unlucky. You have a lot of, you have a very repetitive structure that increases the chance that you can find something similar in the database. Here's a more devious example where the user is interested in the parking space in the background, but the system actually fires on the bus in the front because if it sees those structures someplace else in the database as well. And you can find more examples. But fortunately, you can actually handle this rather easily by detecting which points or which features lie on repeating structures. So if here, for example, assuming that you would find a place in your 3D model where those 4 features are inliers to the pose, and assuming that you find another place in your model where those 4 features are inliers, and another one, then you see that the same set of features is geometrically consistent with multiple places in your database. So that gives you an indication that this is a repeating structure, and you can just ignore it. While if you only observe this geometric, this inlier relationship at a single place, can be pretty sure that this is a valid, unique structure. And if you just add this into image retrieval or 3D method, then you can get a nice boost from a baseline that actually didn't perform that well to something that gives you state-of-the-art results. And again, there's more on outlier filtering via using by using covisibility or geometric constraints, or using place recognition based approach for scalable localization. I'm not going to go into details. Any questions on this part? Hmm? So the question is, if you go to the approach where you have features on the ceiling, that actually gives you more constraints, because you know that you can the scale of the features of correct feature mesh has to be in a certain the scale change has to be in a certain interval, so you can use this. The gravity. Yeah. Well, but you still end up with a rotation around gravity, right? Maybe I'm not fully getting your question. It's a 2D registration problem nonetheless, right? But do you need the feature orientation? Yes. Now I get the question. If you're looking at the ceiling, it still reduces the 2D alignment problem, because you're looking most likely at a planar surface. So you could directly model this as everything lying all points in it on a 2D plane, and then just computing a 2D alignment. And that it's a slightly different formulation, but still a similar problem. Does it answer your question? So the camera height is relative to the ground plane. So, but you can compute a local ground plane, right? So you can, yes. So we actually did this on San Francisco, where we had images captured from a street view vehicle, so you can locally fit a ground plane or get a height map, and then you express the height of the camera with respect to this height map. Yes? Yes. Yeah. So that's a good question. The question was, this thing is evaluated on a landmark recognition task, where essentially the decision whether a landmark is recognized is based on some ground truths over things that are visible in the image, and you need to hit the right thing, and whether you get a different result if you actually look at pose accuracy. And that's true. We had a paper here at CVPR where we actually generated ground truth poses for San Francisco. That changed the picture a bit. It depends a bit on the task that you have at hand. The paper was the one that Aki presented in the morning on the question whether you actually need large-scale 3D models. And if you, we can take this offline, I think, if you want to know details. Alex, if it's fine with you, I'll take 5 more minutes and then. Okay, cool. So the second to last topic is localization on real-time localization on mobile devices, where the idea is you would like to do localization on a device that has less CPU, GPU, has less storage, and where energy consumption actually matters. and at the same time you would like to do things in real time. And if you do AR, VR, you actually care about spatial temporal consistency, so you don't want your pose to jitter because you have a slightly different estimate. And the problem here is that all the methods that I talked before are not fast enough to be run independently per frame. And the key idea to still do localization in real time is that you decouple the real-time tracking of a camera pose with localization. And this is illustrated in this video, where what you can see here is that you get a location estimate every now and then, shown by the lines that connect the camera pose and 3D structure, and in between you do local camera pose tracking using SLAM. So the general outline of this algorithm is you have this fixed size 3D model locally that you use for tracking, and once you get to the edge of that model, so you need to extend this model, you take this keyframe and then try to estimate the pose of this keyframe globally. So you assume that you have a known 3D model, you run any global localization method, and then take this information and feed it back as a constraint into the local SLAM approach to prevent drift. And the simplest constraint that you can use is you take the pose that you computed and you say, look, this pose should be here, adjust the model so that you get this constraint. A slightly more relaxed constraint is to actually look at reprojections. Say, those are the inlier points that are used to estimate the pose, and I would like those points to project close to the image measurements that correspond to them. And let's compare them. So this, what you can see here is the red is the ground truth trajectory that we got from Structure for Motion by including the Curry images into a larger model. The yellow curve is what you get if you just localize once and never do an alignment at all. And you see that the pose estimate drifts because there's drift in local tracking. The blue curve is what you get if you enforce that the positions in the local model are consistent with the positions in the global model. You see that this reduces drift, but there's also something weird going on there around the text. And this is the green curve is what you get if you use the 2D, 3D matches as constraints to prevent drift in your local mapping. And it works equally well except on this one part here that's shown in the trajectory. And what's happening here is that the user is walking around the structure that's particularly close, and then he's seeing buildings that are 20, 30 meters away. If you're far away enough, you can wiggle your pose by a meter or something, still get a good reprojection error, so you have a high uncertainty on the camera pose. And that's causing this jitter there, because the camera pose that you get you can't take them for face value. There's a inherent uncertainty in them. And if you assume that there's no uncertainty, you have problems. This still doesn't fully solve the problem of limited compute and memory, because if you go to larger scenes, you would still need to store them someplace, and localization would still, again, take longer. And there are two approaches to this. The first is to use a server-client architecture where you send images to a server, and the server gives you the information back, and this works as long as the latency of sending and receiving information is small enough that you don't accumulate too much drift locally. The other approach is to compress your 3D map and then store a compressed version of this on the device. And a simple map compression scheme is you only use a subset of points. And it's the same reasoning as before, you only need a subset of matches for accurate pose estimation. There's an interesting trade-off between the model compression and camera pose accuracy that's shown here. The x-axis is the percentage of points that you use. The blue curve is the number of keyframes that you can localize. And as you use less data, you lose more and more matches, you can localize less frames. But the red curve is essentially the localization accuracy, which remains rather constant because you actually don't need to localize every keyframe. As long as your local tracking is stable, you're fine. And this allows you to go from 130 megabytes for one trajectory of, I think, 1.3 kilometers to 20 megabytes. If you look at it visually, there's very little difference in the reprojection of the points. So this gets you down from 130 megabytes to 20 megabytes. You can further compress a map by compressing descriptors, and you can do this actually rather aggressively and still get a reasonable pose accuracy at about a few megabytes per, for reasonably sized maps. And again, there's more literature on this part for more mobile localization that I'm not going to go through. These things are links to the papers, so if you want to know more, please look at the papers. I want to conclude my part with a challenge. So one thing that we're going to release soon is a paper that describes how bad things work if you look at if you try to localize nighttime images against a daytime map. So what we have is we collected a set of nighttime images. For each nighttime image, we have a corresponding daytime image taken from around the same position. We're able to localize every daytime image, but active search would give you like half of the nighttime images at most. If you do build local 3D models around the queries, you get to, I think, 60 to 80% of the queries localized. And this is the good data where you took nighttime images with a software HDR camera, so you get well-lit images. The same paper also contains a slightly different data set where we have both still nighttime changes, but also appearance changes caused by seasonal changes. And again, we have ground truth poses for this. And we made a very interesting observation here, which is we can actually solve most conditions pretty well, at least for the data set that we had at hand. Sun or strong sun is a problem, especially if the light falls into your sensor. But night is a very, very strong problem, especially on this data set, where you have motion blur, where your exposure setting is not that good as when using software HDR. So you can do a bunch of tricks to increase the localization rate, but it's still a hard problem. And we hope to release the papers soon on arXiv, and then we'll also at some point release the data set for you to play around with this. And yeah, thank you very much for your attention. One final question. So the question was, what's the limitation for day-night? It's a combination of feature detector and descriptor. So we observe better performance if we extract descriptors densely, but of course this is not scalable. Especially storing those is not scalable. So I believe that there's no existing method that currently handles those scenes well, at least none that I know of. That's why I released this data set to hope that someone finds something better. Okay, thank you very much.
Sorry about this, let me just try and keep the resolution right. Do you know how to fix this? It's not quite this resolution.
Did you? Do you actually want to have it moved?
Go full screen.
I can do presentation first.
Yeah.
Just unplug this.
I'll do this. Okay. Hi everyone, sorry about that. Let's get started on the last section of this tutorial. So I'm Alex Kendall and I'm here from Cambridge University. I'm going to be talking about machine learning for visual localization. So hopefully this is a natural extension to what you've heard so far. In case you've just walked in, this talk's all about trying to get a 6-degree of freedom camera pose from an image, from a query image in a previously explored area. So I think there's a few key assumptions that I want to test in this talk. I think that Torsten's given a great introduction of some point-based feature methods, but I think there's some ideas in there that maybe there are some other ways to localize, and maybe there's some orthogonal line of thought that I'd like to question. So first of all, I'd really like to pose the question: are point-based feature descriptors the right landmarks to be using for localization? A lot of the problems that have been discussed in these talks is that these features aren't that unique, and actually getting really good matches with them takes a number of features. We have to do things like ransack, we have to do lots of filtering, and we have to store a very large map of these features. And we have to do all these things to get a pose estimate. Now, can we do better? Can we use features which are better than say SIFT, ORB, or SURF, these sort of hand-engineered features that we're using today? So I don't know if anyone can localize this image here, but this is an image of our university back in Cambridge. And the way that we might localize an image like this is through a whole bunch of things that don't just involve single corner features. We don't look at the individual spires and windows, but we take in the whole image as the entire context of the image. We can detect contours, shape, structure of the scene, and all of these to build up a representation that's perhaps more contains richer information than these individual features on their own. So I think that's one of the core ideas that I've been reflecting on is actually, is there a better way of building these descriptors? And as we've been hearing for the last 5 years, perhaps machine learning is the way to go. It's going to be very hard to hand engineer some descriptors that can describe all of these things that we use as humans to localize, geometry, shape, contour, appearance, these kind of things. And so maybe machine learning's the tool to be used here. The next point that I'd like to raise is, should our maps be Euclidean? In these previous methods, we've been talking about big structure from motion models that we try and register to. You know, there is work being done in quantizing them into visual descriptors. But I think there's this general idea that perhaps our maps can be not just quantized Euclidean areas, but perhaps we can have a better feature space than simply a three-dimensional structure from motion model. I think this is an easy argument to make because if you just simply plot a heat map of where we go, then it's not uniform. It's very peaky. You know, we tend to walk in streets, for example, and not everywhere is important as everywhere else. And there needs to be some kind of I think the map representation could do a lot better than simply based on 3D structure. So that's the other assumption I'd like to test is, can we learn an embedding or a description of a place that is perhaps more efficient than 3D space? Now, it's always good to consider how we do this ourselves or how this happens in the animal kingdom. And this is actually a really interesting story in localization. We don't know very well how humans localize, but in fact, in 2014, the Nobel Prize was awarded to Edvard and May Moser from Sweden, I think, and John O'Keefe. And this is so very recently, only in 2014, this was the Nobel Prize for discovering the method for localization in mammals. And basically, this is down to two types of cells, both place cells, which fire depending on our position and orientation, and is more of a topological localization method. And these are found in the hippocampus. And then also grid cells, which these encode more fine-grained Euclidean geometry and is more to do with relative pose to different objects in a local Euclidean scene. And so it's interesting to reflect on how this happens in biology, where there is this disconnect between local Euclidean understanding and also a topological place recognition. And the brain's able to do this pretty reliably at large scale. So to give an overview of this talk, I think this is a great slide to describe the contents of how, perhaps divide up how localization exists today and what the literature is for machine learning for localization. So we've been hearing about 3 different steps in metric localization. We have this feature extraction step, which Torsten described beautifully about taking out point features. Then we have a landmark registration where we've got to associate these features with a 3D model. And then finally, we've got the 6-DOF pose estimation, which in Torsten's talk involve things like filtering, ransack, these kind of ideas. So in my talk, I'd like to introduce 2 more methods. The first one is to do with scene coordinate regression. And this is a method which basically does these first 2 with machine learning. And it tries to solve the feature extraction and registration problem with a machine learning model. So that's the first part. Then the second part, I'd like to consider, well, can we actually learn the entire pipeline itself? And can we go straight from images to a 6 degree of freedom pose estimation and actually learn the entire thing with deep learning? So let me kick off the first part. So this is all about scene coordinate regression. So what is that? So scene coordinate regression is the idea of, can we, for a given image, can we determine the 3D points in a given coordinate system of each pixel? Now this can be thought of as solving the registration problem. So not only are we simply getting descriptors that we need to match, but we're actually matching them to a 3D model. And so this is a picture of a scene from Jamie Schotten's work, where the RGB colors are corresponding to the XYZ of the scene. And so you can see that. So in the following slide, this is showing an example of how the system works. So we go from an input image. This middle image is showing what the ground truth looks like when you start to think about every pixel being an XYZ coordinate. And then finally, this is from the paper presented a few days ago at this conference, was what state of the art is today of being able to predict scene coordinates. And so this is a very neat idea because it's asking a machine learning model to be able to predict the correspondences itself and actually say, for each pixel, this is the XYZ location. And once we have a number of these, we can then use them to aggregate and to get a hypothesis for our camera pose. So this idea was, at least the first time I heard about it, was from Jamie Schotten's work, first presented back at CVPR in 2013. And what they proposed was to collect some data of small indoor scenes using Kinect Fusion from a Kinect camera, an RGBD camera, and use Kinect Fusion to create ground truth camera pose labels. They then suggest to train a regression forest to be able to go from these RGBD images to predict scene coordinate labels, and they train on depth-aware features. So their features fed into the forest were aware of their depth, and they were trained on sort of very basic random forest features. But what this forest was trained to do was to predict these XYZ locations for each pixel. And so this is really bringing the registration problem inside a machine learning model. And so in this initial work, it was very noisy. Using random forests produced very noisy camera hypotheses. And if you were to pick a random sample of points and try and generate camera hypotheses, you get a very noisy collection as shown in this image here. So the idea then is to take to use RANSAC and to randomly sample and reduce these until you get a set of inliers that match with a credible hypothesis. And so this was the idea that Jamie Sheldon presented, to take this RGBD images, run them through random forests, and get these inliers to infer camera pose. As you can see from the inliers, it's very sparse, so you don't get sort of a globally consistent estimate with this method, but it can be fairly robust when you run it through this RANSAC pipeline. So the data set they showed these results on was a whole bunch of 7 small indoor scenes where there were about 2,000 to 6,000 images in each scene and a few thousand test images. And these scenes ranged from about 3 by 3 meters sort of spatial area within office spaces, kitchens, stairwells, these kind of scenes. What they could show is they could show that this was able to outperform SIF-based approaches where you take key points and try and register it to a 3D model. And so this is showing that in these small constrained environments, actually learning these first 2 stages in the localization pipeline and learning the registration can outperform these traditional methods, which is a really exciting result. So the baseline sparse RGB was the baseline method of matching to a structure from motion model. The 3 results that I'm showing here from their paper are using different types of depth features into the random forest networks, and you can see that they achieve a fairly good percentage of frames to be under 5 centimeters and 5 degrees angular error. So this is these metrics are also looking to go beyond the location recognition, but also now to what we're really after is metric error, and how good is the metric relocalization. So following this work, there's been a whole bunch of very exciting improvements, which I'm just going to briefly describe to you. So the first one is a paper called Random Forest versus Neural Networks, What's Best for Camera Relocalization, and that explores, that's follow-on work exploring doing that with both random forests and neural networks, and which one is actually better to generate these scene coordinate, to regress the scene coordinate labels. And interestingly, they found that random forests in their setting worked better, and that although neural networks were able to produce a better estimate of the scene coordinates, when you then pass it through RANSAC, it produced worse performance. And they have a method for combining them both. Another paper following on from that was called Uncertainty-Driven 6D Pose Estimation, and this was presented at CVPR last year. And the exciting thing here is they showed that they can actually do this with just RGB images. So this is throwing away the depth modality and now doing localization with just color images. And they could show a similar thing where they can learn to regress score labels from there. And then finally, I'm sure you've all seen the paper this year at CVPR, which then looks to complete the end-to-end machine learning architecture and then actually formulate the RANSAC part as a differentiable machine as well. And that's very exciting because I'm showing a picture of the results at the bottom from that paper, and you can see that they get much more of a dense inlier set where you get really a consistent estimate of the scene coordinate labels on the whole scene. And this is now using deep learning, so it's going beyond the very basic features you get out of random forests. So to summarize this section, well, what are the good things about this? Well, by going straight from the images to a registered scene coordinates, this is great because now we don't need a Euclidean map. We're not relying on a 3D structure from motion model, but instead we're relying on a machine learning model to implicitly encode features and say, learn a mapping from the pixels in the appearance space through to a registered 3D context. And so this is great because it scales efficiently, because this map is now encoded in a more efficient feature space. But what are some of the problems? Well, learning scene coordinates today doesn't use global context. So this is applying a machine learning model on a local area to try and describe, say, for each pixel, describe the local scene coordinate. But we're still not getting to the global context that in the motivation I said that we really want from these machine learning models. And secondly, perhaps you could argue that the paper this year addresses this to some extent, but in general, the inliers are still noisy, and perhaps ransack isn't such a reliable technique. Maybe there's a better way that we can more cleverly choose which hypotheses to sample from. And so this is perhaps motivating further work here. So that brings me to the second part of the talk, which is about now can we go from directly from images to camera pose directly through a machine learning model. But first, are there any questions about the scene coordinate regression section? Great. Okay. So in this work, I'm going to start talking about a model that we proposed a couple of years ago at ICCV called PoseNet. And this as an initial model is really after the idea: can we learn a mapping directly from the input image to the 6th degree of freedom pose? Now this is a very complicated mapping because it's going from appearance space to a space which is linear with respect to pose. But what we're able to show is that you can actually learn this with a deep learning model. So what we did is we took a pre-trained classification model. It could be any of them, but in this case we chose GooglerNet and trained it to regress the 6th degree of freedom pose from an input image. And this was trained with a simple regression loss function where we had a weighted sum of a Euclidean loss around position as a 3-dimensional XYZ vector and an orientation as a 4-dimensional quaternion. And so yeah, this worked pretty well out of the box. It was able to we were able to leverage a pre-trained model on ImageNet. So we had some features which were a fairly smooth manifold, and then fine-tune it to become a regression network. So this is showing the kind of results you get. So this is a top-down view of some localization data that we were trying to train on. In green is the training data. So you can see that there are a number of distinct sequences from different times of day and different weather conditions. And then blue is the testing sequence. And so this ground truth was obtained through a structure from motion model with bundle adjustment on the entire data set. Now in red is showing the results from PoseNet, and you can see that the network's able to, one of the exciting things I thought when I first saw these results was it's able to actually regress a somewhat smooth pose manifold. So it's not simply learning a classification result. It's not taking a query image and trying to find the nearest neighbor in the training image, but it's able to interpolate successfully and learn a manifold which is somewhat smooth. The other great thing about these features is that they do use a lot more context. So because we're taking input images and we're learning a mapping straight to pose regression, these features through the convolutional network are aggregated from the entire image. So in this example with the GooglerNet architecture, we're taking the image and we're passing it through a number of layers, and we're convolving and forming features which rely on the entire image. As we've seen with other deep learning fields, these features are able to fire off shape, global context, appearance, and they're much more robust to the sort of nuisance variables that we observe in real life data. And so these are some results showing that we're able to register to a coordinate system in a way that's much more accurate. We can deal with blur in these situations, such as blur when you have heavy occlusion. The third example with dusk is a situation that is very, very hard for point descriptors. And what the model is able to do is it's able to build descriptions based on, or a feature based on shape and contour. And that by using these features, it can work in situations like this. And to a limited extent at night. So I'm looking forward to testing it out on Torsten's dataset when it's released. Yes. Of course. Mm-hmm. So there is overlap with spatial location. However, the sequences are taken from different times of day, so they are different in appearance space. So you can see in the left and right images, the weather's going to be different. There's going to be pedestrians and other clutter that's going to be different. So it's not the same in appearance space. There are some examples which are very similar in pose space, but then there are others that aren't. So there is an aspect to that, yes. I just want to show some results from another paper that was placed on arXiv last year, and this paper obtained a data set which was sort of like an adversarial data set to some of the point-based feature localization methods. So we know that they really struggle in indoor environments when you have, say, some very featureless surfaces that might be non-Lambertian. And there's some images from some of their data set. We have an area which is very much void of features. And what they could show is that, at least the methods they tried using SIFT-based features, they didn't work. They couldn't form a registered 3D model. I think they obtained, I'm not sure how they obtained ground truth, but they used another method, perhaps. But one of the exciting things is that the features learned from the deep learning model are able to localize in these kind of scenarios. So this is more evidence that the features do actually learn contour, appearance, shape, and things at a higher level than simply corner features that individual SIFT or SURF landmarks might capture. And then they go further to describe a model which I'm going to discuss soon, which actually improves on the original PoseNet model and gets the error down to almost a meter and a few degrees. So some more insight about this model, which learns straight from camera pose to straight from image to camera pose, is you can also start to look at the saliency. So the saliency of the model is asking for each pixel how much does it affect the output. So which pixels are most important in determining the pose. And this is showing some results over a number of images, and you can start to see some really interesting patterns when you look at these saliency images. Firstly, by training straight from images to camera pose, the model learns to not only grab corner features like in the left image like the spire, but it actually looks at the sky and it looks at the context and it checks that yes, the sky is at the top and that it's not just the edge, but it's also the context around the edge, not just these corners of the spires and the facade. In the middle image, you can see that dynamic objects like people and cars are attenuated, and that the brighter white color indicates more saliency to the facade, which is perhaps more reliable for localization. And you can see a similar result on the right, where it attenuates the pedestrians. So this is more evidence that the features that we can learn are perhaps more powerful than these individual individual point feature landmarks. I'm pulling some results here from another paper called Towards Convolutional Neural Network Map Compression for Camera Relocalization. And this paper is interesting because it looks at the relationship of how these networks scale. So this is another benefit of this method, is that we scale almost constantly with an amount of training data. So the more training data you pump in, at test time, we're still running a single forward pass of the network. So it has a constant number of network parameters and a constant inference time. But as you pump in more training data, of course, as these graphs show, the results get better and you start to learn a better representation for that data. And so one of the exciting things about these networks is they scale almost constantly with training data for a given network size in terms of inference penalty, but you can, of course, improve performance by adding additional training data. So to summarize, the original PoseNet model is fairly robust to different aspects because it can learn features which are richer than what we might get from point features. It has very fast inference and a very small memory size because it's able to learn a compact representation of the map with a deep learning model. But I'm going to discuss the accuracy soon. Unfortunately, the accuracy is and I'm the first to admit this, it's not quite at what we get from these feature-based methods. And there's also a difficulty between learning both position and orientation in the same model, and this is a multitask learning problem. So to go over the multitask learning problem, the way that PoseNet was originally trained was with a model which trained on both Euclidean loss on regression on position and orientation. And the problem is that you need a weighting factor between these to learn both of them effectively. And this graph shows the performance of both position and orientation as you vary this weighting factor. And as you can see on the far left, you're basically just training position, but your orientation performs very poorly. And on the far right, you're just training orientation, but your position performs poorly. And so there's an optimal weighting where you get the best performance. And you can understand the relationship between these, because if you have geometry, which is very far away, then you obviously care about rotation more, because position isn't going to affect the reprojection error very much. But if you have geometry very close to you, then you can care about translation more. And so this is what, well, at least in the original work, was required to be hand-tuned. So a few days ago, we presented a paper which tries to extend this and tries to either learn or infer the weighting from the scene's geometry. So we propose to do this by introducing a loss function, which takes the 3D geometry of the scene, whether it's from a depth camera or a structure from motion model or otherwise, and train rather on the Euclidean loss of the pose, rather we want to train on the reprojection error of that geometry. So that's saying, can we take these 3D points and take our network's estimated camera pose and ground truth pose and reproject the 3D points to both of those spaces and train on the disparity or the registration loss in image space. So this is a loss function which is aware of the geometry and naturally combines both position and orientation into a single scalar regression value. So now I'd like to talk about some results. Firstly, just to introduce some data sets. The first data set we're showing results from is from the Cambridge Landmarks data set. This has 6 scenes from around Cambridge University with 8,000 images, and the scenes vary from around sort of a small shop facade to an entire street. And so they're small urban scenes. The next data set is the one I discussed earlier with 7 small indoor scenes. And then finally, the Dubrovnik dataset, which has been extensively discussed already today, and this has 6,000 images from a variety of camera types around a small town. So when we start to look at the results, at the top I'm showing where it says linear sum, that's the results from the original PoseNet work. And you can see that on small urban scenes, we're able to get the error down to a few meters and a few degrees. On Dubrovnik, which is the larger small city data set, the errors are over 10 meters and about 5 degrees. Now, I won't run through all these results, but jumping down to the most recent work using this reprojection error as a loss function, we can now pull the results down to, with the median across the test set, under a meter relocalization error and about a degree. And this corresponds to 90% of the data, of the query data being localized in under 2 meters and 5 degrees error. Again, on Dubrovnik, the localization is worse across this largest scene, but we're able to get 8 meters and 5 degrees. And so this is not quite good enough for augmented reality applications, but because it's more robust and efficient, it's starting to become appealing for sort of a coarse localization estimate that you can use. When you start to compare it to the active search method that Torsten introduced, it's still quite a wee way off, maybe on the small scenes a factor of 2 off the performance of that. So the performance is coming down, but it's still not there to what the traditional methods can do. But we're hopeful with some more research that this might come down even further. But you can start to look at other aspects of the network. So like I've tried to show some evidence for, it's perhaps more robust, and that initial question that I posed to you of what is the best map representation? Should it be Euclidean? Well, by learning a feature representation and learning this map space, we can show that it's also more efficient. When you compare the methods, PoseNet only requires a very small resolution image of 256 by 256 pixels, and 2 milliseconds is a single 4 pass through a neural network to localize. On the other hand, these geometry-based methods require tens or hundreds of milliseconds and very large resolution images to compute their features. But on the other hand, the trade-off is in today's performance, they also get a far more accurate registration. So there are lots of questions here of how can we further improve performance, and how can we scale it? How can we get the performance we see on the small urban scenes on the larger, say the Dubrovnik data set? So finally, I'd just like to run through a few more papers which extend this work and show other interesting aspects of this machine learning approach of going straight from images to camera pose. So there's work that shows how to model uncertainty in these networks, how to understand the compression and the space that we learn to map the map in, how to improve the context of features, video localization, ego motion localization, and localization over RGBD frames. So the first one, I'm very excited about this work, which is a paper which shows how to improve the context of these features. So in the initial motivation, one of the things I questioned is, can we improve the context of the features and go beyond what these small-scale, say, SIFT feature landmarks can give us? So what this paper proposes to do is takes this original idea of mapping images to camera pose, but instead of the original network simply pooling these features and then applying a simple regression, what this proposes to do is have a recurrent layer that has an LSTM that trawls across the spatial dimensions of the feature. And so this is a way of spatially aggregating the feature and trying to have a better way of understanding the spatial relationship of the features in the image. And so one of the exciting things they can show is across some of these data sets I've introduced, they improve the metric localization performance by about 5 to 50% across the data sets. So this shows that I mean, before I was talking about changing the loss function to use geometry and a reprojection error. So this paper is a complementary idea where it develops on the architecture and tries to improve the spatial context of these features. It shows that there's a lot to be gained by going from just out of the box classification architectures, but now going to architectures which can gather more context in the features. The next one I'd like to talk about is in modeling uncertainty. So this is a paper which is able to use a Bayesian neural network to understand the uncertainty in relocalization. And one of the nice things is you can show that this uncertainty is a really good estimate for the metric localization error. And then secondly, it can also show if the model is familiar with an image it's shown. So this is known as the loop closure problem. Have I been to a place, have I seen this place before, or is this a new place? And model uncertainty, the graph on the right shows a very strong correlation between model uncertainty and distance to, and relationship to that image. So if it's a new image from a new scene or outside the scene we've trained on, then this is a really nice way of detecting that from these models. And when you start to look at the images at the bottom from the Cambridge Landmarks dataset that are very uncertain, you see that they're like the adversarial examples we know about: overexposed, nighttime, occlusion, or featureless areas. And so this is uncertainty in neural networks is a way to detect that. The next work I'd like to talk about is extending PoseNet to work over video sequences. So this is an idea of having PoseNet and then taking the feature vector at the top and running a recurrent model on top over video. And what they can show is that this acts like a filtering method, and it's able to smooth the estimate over a number of frames and give a nice temporally consistent pose estimate. So just to show some results on the right, you can see that the yellow is the ground truth, and in red is the original per frame PoseNet, and then their network vidlock is able to give in blue a much smoother pose estimate that filters and has some temporal consistency by modeling the features with a recurrent neural network. And lastly, some work that I can mention is this work's all about using RGBD images. And so in an indoor environment, they take images such as from a Kinect camera and try to localize. And what they propose to do is have two separate networks, one that operates on the color features and one that operates on the depth features, and then combine them in feature space later on, and then again try and regress camera pose. They show an incremental improvement over just the RGB network. So to summarize this talk, as any good talk, I hope it provokes more questions than answers, and maybe these are some points that I've been thinking about in my research that I'd like to share. So firstly, what these results can show is that actually maybe learning a map representation can give us a more efficient map than Euclidean, and maybe we should consider being able to learn something which has a space which is more efficient and more effective to localize in. Secondly, using convolutional features allows us to be more robust to environmental challenges, so things like occlusion, night, daytime, lighting, these kind of things. If we have it in the training data and we can learn features which have global context, then this is going to improve our localization result. But there's so many more research questions, which I hope this might motivate some of you to take on board. Firstly, the accuracy is still not as good as these traditional methods, so how do we really push the boundaries here and try and get the accuracy down to an area that's almost good enough for augmented reality? Secondly, how do we scale it? I've been PoseNet out of the box doesn't work on the San Francisco data set, and so how can we extend these models up to a city scale? How can we learn this map online? So at the moment, this requires offline training from data, and then we can go and relocalize, but it'd be really interesting to consider localization in more of a SLAM perspective. And then finally, how do we even obtain these data sets? Because if we're using structure for motion for labels, then perhaps that might set a lower bound for the accuracy we can obtain. And so I think there's some really interesting questions about active learning and how we can effectively obtain large data sets. So thank you. Here's some of the papers that I've worked on, and maybe I can talk about in more detail, or I'm happy to answer high-level questions about the other papers that I've read. But thanks for your attention, and I'm happy to take any questions. Thanks. Yep. Yeah, so I think, I mean, there's been some really interesting work on generating images through, for example, generative adversarial networks, GAN networks, to generate different images from different scenes. I'm sure that would be a really interesting approach. Other synthetic augmentations you can do are, if you can build a dense 3D model to be able to reproject novel viewpoints. All these kind of ideas about synthetically increasing training data, I think, are great. I mean, you've got to be careful not to introduce bias through this synthetic generation, but yeah, I think that's one way of tackling the data problem. Yes.
Hi. On the in the loss for PoseNet, in your rotation loss, I noticed you're trying to regress a normalized quaternion, and I was wondering whether you had tried just trying to regress a quaternion that you then normalize in the loss, which gives your network a bit more freedom, and whether you tried any other rotation parameterizations.
So we have tried both a normalized and unnormalized quaternion, and in practice we didn't notice anything significantly different in the results. So experimentally we didn't see any difference there. Perhaps when you start to converge, the Riemannian manifold and the Euclidean manifold start to become quite similar, but in an unconverged state there might be an issue there, but experimentally we don't see one. In terms of rotation representation, I think this is a really interesting problem. If we could move to because obviously quaternions are over-parameterized, and within the rotation sphere they doubly map each rotation, which is an issue. So moving towards something like learning directly an SE3 matrix or something like that would be nice. We've tried to do this. You can, for example, learn an exponential map, but this has a lot of these methods, like exponential map, have a discontinuity or a point they break down, for example. And so finding a rotation representation which doesn't suffer from a discontinuity or doesn't have something that repeats around, for example, 2 pi, like axis angle does, this is challenging, and these are all trade-offs to make. In our experiments, we found quaternions to work the best, but I very much think this is an open research question on how to parameterize rotation.
Did you say you tried the rotation matrix, or that's something you'd like to try?
No, so we've tried the rotation matrix by learning a 3-dimensional vector and then applying the exponential map to an SE3 matrix. Okay,
you haven't tried to learn directly the 9 parameters of a rotation matrix.
So to do that, you need to constrain your matrices to be orthogonal. That's non-trivial.
You weren't constraining your quaternion to be normalized. You were training it to be normalized. So you could, if you simply try to train the rotation matrix and then project it onto SO3, once you've regressed it, that could potentially work.
That could. I'd be interested to see some results there. It's not something we've tried. So the question was about how it works if we train on one city or one scene and then move to another one. So obviously this is relocalization, so it can't localize an area it doesn't have data for. But the interesting thing is the map you learn from one city, like you see in a lot of transfer learning papers, provides a very good feature to use in another one. And so one of the things we found is that training on a lot of data for one scene will provide a very good pre-trained model to use in another one. In another scene, and so the features you learn and the low-level features tend to be complementary between scenes. But of course, the absolute coordinate frame and the regression you apply at the top will need to be learnt per scene. Torsten, what's the plan from here? Sorry, we might have to take the rest of the questions offline. But thanks very much.
So the plan from here would be, if there are no further questions to Alex specifically, if there are any questions from you that you would like to have the opinions from all of us, so more broad questions about the relation between the individual parts of the tutorials, we'd be happy to answer this. If there are no more questions, then we would be very thankful for you to attending our tutorial. But yes, if there are questions, please feel free to ask them. Okay, that's you. Specific question is you. Sure.
So this is a question about the end-to-end learning part for post-regression. So once the feature correspondences are established, it's a very deterministic problem to get the posts out of it. And I'm wondering why in that case would you try and do end-to-end learning, because at that point the problem can be solved geometrically.
So I think this comes to the motivation at the start about, firstly, do we need to have a 3D or Euclidean map? And so yes, it can be solved geometrically, and maybe this is appropriate on a small scale for accurate small scale relative pose, but on a large scale, I think there are much more efficient map representations we can have, and we can form features that aren't explicitly geometric. They may be more topological. And this is something that's going to be very hard to hand engineer. So the motivation there is really to try and learn a map representation, which is, maybe a feed-forward neural network isn't the best way. It's one way of doing it, but learning a map representation which is more efficient. Are there any more questions? Yes.
Hi, I apologize if this was already covered in the morning talk. I was unable to attend. But for landmark recognition, my understanding is that the work last year, which uses the RMAC feature descriptor and trains a Siamese network, at least in 2016, that was the state of the art on the Oxford and the Paris data sets. And I was just wondering if anything was covered about improving on that. That's the first question. And the second question is, we've seen that approach does really well on man-made structures, but on natural landmarks, presumably because there aren't like very distinguishing features, it tends not to do as well. And so I was wondering if there was, like what your thoughts were on research as far as natural landmark recognition goes.
So, is it working? No. So about the first part of the question, it was about improvements on top of end-to-end learning of a representation such as RMAC. Well, one thing is that NetVLAD, that is somehow like a concurrent work. It was applied and trained on location recognition on kind of different data sets, like Street View data sets. So that's an embedding that also in the work it's shown that it's better than just doing global max pooling. So it's an embedding that has some extra cost to train and also some larger memory requirements. But because of the finer matching it in terms of local descriptors that it does, it obtains better performance. So that's one case. Other cases, such as work that was part of CVPR 17, is including a layer that is kind of attention model that better adapts and better weights the activations at each location of the feature map. So about the second part of the question about, it was about matching natural landmarks, right? And not like man-made buildings, which is something indeed that we have not considered in prior work. However, what we observe is that already this is something that was not handled well with local feature-based approaches and geometric matching, and already like CNN-based representation gives you better features discriminative enough like to capture such kind of variances. So like that's a better way to go, but indeed there is nothing considered so far like in
Thank you.
the literature. Okay. So thank you once more for attending our tutorial. So since there are no more questions, we'll finish this for the